So we'll move on to exercise 1.3. Before getting to it, we have all of these definitions to get through. The first is that the set N is defined as the intersection over all inductive sets, or said another way, it is the smallest of inductive sets. It will turn out that this is in fact how we construct the natural numbers, and so this exercise is actually extremely important, but we don't quite know that yet formally, so to speak, but it is good to keep your eye out for it. Other definitions are that the symbol that we use for 0 will be an abbreviation for the empty set. The symbol that we use for 1 is an abbreviation of the set of the empty set. The symbol that we use for 2 is an abbreviation of this set, and so on. Now, what is the pattern here? The pattern is that for every number, the next one is the previous set union that number, basically. So, if you think about it applied to, let's say, the empty set, then or the number is 0, right? So 0 plus 1, according to this definition, is the empty set, since that's 0, union the set of the empty set. This simplifies to just the set of the empty set, and what do you know? That is in fact identical to our definition of 1. If you repeated the process, you would find that 1 plus 1, after doing all the relevant calculations, would come out to 2. And so on, so that this really is a consistent, good way to identify the plus 1 operation. Moreover, if I particularly tried to not write sets as much as possible, if I tried to write these numbers but not writing all of these confusing sets that are within them, then in the case of 1, I would not write the set of the empty set, I would write the set of 0, trying to get rid of sets as much as possible and express this in terms of numbers. I would say that 2 is the set of 0, comma 1, and if we did the calculations, you would find that 3 is indeed the set of 0, 1, 2, and more generally, any number n is the set of all numbers less than it. Now, that's actually a theorem to prove, and we will prove it at the end of this exercise, but it's a good thing to sort of keep your eye out for as well. Okay, before moving on to the proof, we need to know what a transitive set is. A set is called transitive if being a member implies being a subset, which typically in normal set theory and undergraduate set theory is a weird thing to say. Elements are typically not subsets. But in fact, here they are. You can even just look at 2 and see that the number 1 is both an element as well as a subset. It's an element because it occurs as one of the terms. It's also a subset because every element of 1 is also an element of 2. So there you have it. This transitive property, in fact, describes at least some of the things that we have already seen here. Now, nothing about it looks very transitive, so I would like to make the following claim to help sort of build up our notion of what a transitive set is. I claim that a set T is transitive if and only if the inclusion relation is transitive in the sense that we typically understand that word to mean. Let's see a proof that this is in fact true. And in fact, I will use this property at certain points in my proofs. Suppose that T is transitive, and A and B in T, we would like to show that A must therefore be in T, right? So I'm supposing that it's transitive and trying to show that this property implies that A is in T. Well, from the definition of transitive, B being an element of T implies that B is a subset of T, and we know that A is an element, so from this it follows immediately that A is an element of T. So I have just shown that if a set is transitive, it has this conditional property, if you'd like to call it that. Let's see how it goes in the other direction. Suppose that whenever B is an element of T and A is an element of B, then for all such elements, A is an element of T. Suppose that it has that property, we would like to then show that T is transitive. That is to say, if anything is an element, then it is a subset. Okay, so let's take an element, and we want to show that it's a subset, where we are assuming that it has that conditional property. Okay, since B is an element, and I want to show that B is a subset of T, I'll do the typical subset style of proof. I will consider any element of B and show that it must be an element of T. But since I assume that that A is in B is in T, then by the conditional property that I have assumed about T, it follows that A is in T, and that's exactly the thing I wanted to show. So there you have it. The transitive property is just the same thing as this conditional property that I have claimed over here. On to actual exercise work in the next video.